All right, welcome to This Explainer. Today we're tackling a massive headache in AI, how researchers have finally cracked the historical performance gap in temporal AI models through sheer scale. If you've ever tried to use an AI to backtest a trading strategy or comb through historical social science data, you absolutely know the pain of trying to keep the model from remembering events that technically hadn't happened yet. Today, we're looking at a huge breakthrough in creating chronologically pure AI that actually performs up to modern standards. Let's get right into it. Here is our game plan for today. We're going to walk through the look-ahead bias problem, how scaling point-in-time models actually fixes it, measuring those performance gains, the real-world economic impact, and wrap up with a concrete action plan for developers. Okay, part one, the look-ahead bias problem, or when AI knows the future. Think about it. Standard large language models are kind of like someone holding a sports almanac from the future. If you ask a standard model to analyze news from, say, 2018 to predict a stocks movement, well, it's already read the financial reports from 2019 and 2020 during pre-training. It already knows how the story ends. This completely ruins the integrity of any historical backtesting because it makes it look like you've built this brilliant predictive model, when in reality, your AI is literally just cheating. This right here is what we call look-ahead bias, or training leakage. It's a huge deal. It completely distorts risk and return metrics because standard models just treat time as this one giant static data dump rather than a strict sequence of unfolding events. If your model absorbs information that was unavailable at the time of the event you're evaluating, your causal inference goes right out the window. You aren't discovering a trend, you're literally just measuring a memory. To put it simply, standard LLM training just hoovers up the whole internet, past, present, and future all mixed together. But point-in-time training? That's a totally different beast. It uses a strict chronological cutoff. The model is only fed text published on or before a very specific date. It is effectively living in that exact moment in time, completely isolated from anything that happens next. Moving on to Section 2, scaling point-in-time models and bridging that performance gap. Historically, these point-in-time models kind of felt flat compared to standard ones. But researchers just proved you can actually brute force this gap closed with sheer volume. We're talking 1 trillion tokens. They took the massive FineWeb dataset, strictly filtered it by date, and trained decoder-only transformers entirely on these chronologically pure tokens. And they didn't stop at just the data. They scaled the architecture itself up to 4 billion parameters. To make sure it was on par with modern standards, they engineered it with a 2048 token context length and a 4096 embedding dimension. Basically, they took the absolute best modern AI blueprints and forced them into a time-locked training regimen. What this creates is a really fascinating, continuous pipeline. They didn't just build one model. They built a rigorous sequence of rolling monthly checkpoints. Starting with a base knowledge cutoff in 2013, they rolled out a new version for every single month, all the way up to 2024. So a model stamped December 2014 literally only knows the world up to December 2014. This lets researchers do real, untainted, year-over-year out-of-sample testing. Which brings us to Section 3, measuring the performance gains and approaching unconstrained AI. So what's the actual impact here? Well, the benchmarks are incredibly validating. If we look at the new PIT-4B model against the older ChronoGPT and a state-of-the-art unconstrained model like Gemma 3.4b, it's wild. On HelloSwag, which tests common sense reasoning, PIT-4B shoots up to 72.2%. That crushes the old ChronoGPT's 43.9% and gets really close to Gemma's 76%. And on Pika and Wino Grande, the gap between the time-locked model and the unconstrained model is basically erased. It turns out the performance hit wasn't because of the chronological training at all, they just needed more scale. But of course, a raw base model only gets you so far, right? It needs instruction tuning. The researchers tackled this using low-rank adaptation, or LoRa. By freezing the base weights, they only update a tiny fraction of the parameters, specifically factors A and B. This is an absolute game changer because it keeps compute costs way down while perfectly preserving the temporal integrity of the base model. You're not accidentally leaking future data during fine-tuning. Plus, they evaluated all of this programmatically on IF-Evol to completely dodge any LLM as a judge bias. All right, Section 4, Real-World Economic Impact, Testing in Quantitative Finance. This is where the rubber meets the road. We can take these chronologically pure models and throw them at one of the hardest out-of-sample tests out there, forecasting stock returns. To measure the actual economic value, researchers pulled text embeddings from historical financial news and ran them through maximum Sharpe ratio regression. This is essentially a method designed to maximize risk-adjusted returns, balancing risk versus reward, while keeping a really tight lid on overfitting. And the economic gains? Absolutely massive. For megacap stocks, the older ChronoGPT base model pulled a Sharpe ratio of about 0.56, but scaling up to that PIT 4B base pushed the Sharpe ratio to a really robust 0.80. That is a huge jump in predictive power. It proves these scaled models are pulling deep, genuinely forward-looking signals from the text, completely free of any look-ahead bias. Finally, Section 5, Action Plan for Developers, implementing the open source pipeline. The best part about all this? The researchers completely open-sourced the dataset construction and the training infrastructure. So here's a concrete playbook for developers to just drop this into their own clusters. Step 1, definitely pin your data sources to versioned releases so your date stamps are rock solid. Step 2, use LoRa fine-tuning for your downstream tasks so you don't corrupt the timeline. Step 3, rigorously validate for temporal leakage using date-stratified value sets. Step 4, keep monitoring the performance gap, especially if you're working in super niche domains. And Step 5, containerize the training pipeline to guarantee your checkpoints are perfectly reproducible. So the big takeaway here is that the perceived cost of eliminating look-ahead bias was mostly just a lack of scale. Researchers seriously don't have to choose between temporal validity and high performance anymore. Now that AI can truly live in the past, and this tech is openly available today, what historical mysteries are you going to backtest first? Thanks for tuning into this explainer, and I'll catch you on the next one.